Hello everyone, in this video we're going to be talking about the halohydrin reactions of alkenes. As the name specify, halo means you're going to be adding a halogen, but hydrin means you're going to be adding water along with it. And they're not only limited to the water, but they are typically called halohydrins because that's going to be the most common method or most common reagents you're going to be using. So if I want to go and write a generic reaction where you got the CH2 double bond CH2. So your reagents here are going to be some sort of halogen, so suppose X2, and that's X2 is going to be either a chlorine or a bromine. And then in addition to that, you may be using some other nucleophile in that case. So, and typically the most common other nucleophiles you're going to be using would be the water or maybe even some sort of alcohol. So what really happens in this particular case, you're not going to have only two halogens added now. It's going to be only one halogen added onto one of the carbons, and the other carbon will get the nucleophile that you're using. So I would have maybe halogen in one of the carbons, and on the other carbon, you're going to have this nucleophile, whichever you are going to be using. So this is going to be still an anti-addition. This is still going to be an anti-addition. However, when we talk about the regioselectivity here, because remember, you don't have the same type of atoms are added onto those double bond carbons, so you do have to worry about your regioselectivity here, which is still going to be Markovnikov's rule there. So let's take an example where the regioselectivity would matter here. So suppose I'm running this reaction where I got this one butene and I'm using a Cl2 with water. So your first step is going to be your nucleophile is going to be attacking this chlorine, which is acting as your electrophile. So typically in Markovnikov's rule, your electrophile would be the hydrogen, but here the electrophile is the chlorine. So between those first and second carbon, where would the chlorine go? Well, at the end of the day, your chlorine would go onto the first carbon, just like an hydrogen would go to the first carbon according to the Markovnikov's rule. But it doesn't necessarily go right away, but rather it makes something similar you have seen in case of halogenation reaction where it makes an halonium ion. So you got the chlorine right here. So that's going to be your intermediate in this particular case. So that would be your chloronium ion. Now, between those first and second carbon, the nucleophile that we're going to be using now would be your water in this particular case. And between the first and second carbon, where would the nucleophile attack? And the answer is going to be coming whichever those two carbons, one or two, have a bigger partial positive charge, or it's on the verge of making a more stable carbocation. So you actually want to have a positive charge on the second carbon rather than want to have a positive charge on the first carbon. So that's why it goes in a Markovnikov's addition. So I could have this oxygen coming in there, and it's going to be doing um, it's going to be attacking from the opposite side where the chlorine is. So that's what makes it an anti-addition. And it's the regioselectivity. It's going to be doing the Markovnikov's addition because your water is the nucleophile. So it's going to be attacking the carbon that's going to be able to have a better positive charge, or is going to be able to make a more stable carbocation, even if you don't really make the carbocation in here. And then this is going to break up here, and then we're going to have these two guys anti to one another. Now, you really have to worry about these two guys being anti to one another if they are both chiral, but if they are not chiral, then you don't really have to worry about it. But obviously, your second group is indeed, second carbon is indeed chiral, so I want to make that water coming out of the page, and in that case, that chlorine would on carbon number one would be going back into the page. But like I said, you don't have to worry about drawing the chlorine back into the page on the first carbon because that carbon is not even chiral. Okay, so that's your one possibility, and your other possibility would have been your water could be going back into the page, and in that case, your chlorine would be coming out of the page. But we'll get to that in a minute. But before we finalize the structure, we gotta go back and redo this acid-base reaction. So mechanistically, what you can do, you can have this chloride, or even you can have the water kind of coming back in there and grabbing the proton. So it doesn't really matter. So then my final product, one of them is going to be where your OH is going to be right there. And obviously your chlorine here is going to be going back into the page. But like I said, you don't really have to draw that back into the page because that carbon number one is not chiral. And your second product obviously would be, what if they were flipped? You had your OH going back into the page, and that would make this chlorine in that case coming out of the page. So that would be your two possibilities. And if I want to go ahead and redraw those, like you would typically see in the exam or in the question, you would not have to draw that chlorine going back into the page or coming out of the page because it's not chiral. So I would just draw a simple bond there. But still, that's going to be a pair of enantiomers there. So that's going to be your question there. Let's take an example here. So when I'm looking at this one, suppose I'm going to be doing something like maybe Cl2 and maybe CH3OH. So not using water, like I said, you don't have to necessarily use water all the time. You may be using some other uh, nucleophile there. So when I'm using this, what I can have, obviously I'm going to have carbon 1 and carbon 2. So where would your chlorine go? So selectivity has to be one way. So chlorine being your electrophile, so electrophile needs to go to the carbon that has more hydrogens to begin with, according to the Markovnikov's rule. So your chlorine would go onto the second carbon, and your this methyl group will go on to the first carbon. So let's go ahead and erase part of that. So suppose my chlorine initially is going back into the page. So what's that going to do to the methyl group? That's going to be making the ether here. That's going to be coming out of the page like this, and that's going to push that methyl going back into the page. So that's one of your products, and obviously you can have it flipped where your chlorine could be coming out of the page now. So if that's coming out of the page, then your methoxy group will be going back into the page, and that will push this methyl group coming out of the page. It's another way of saying you are still going to be making a pair of enantiomers or a racemic mixtures in this particular case. And you're not going to be always making the racemic mixtures. What if you have another chiral center somewhere in the molecule? Then they're not going to be racemic mixtures, but in that case, they would be the pair of diastereomers, so something you want to be careful with. So the take-home message on these halohydrins, obviously your nucleophiles most commonly would be water, but it's not only limited to the water, and you would be using you would be doing an anti-addition through the formation of polonium ion. And in terms of regioselectivity, it's going to be the Markovnikov's addition. But remember, it's not the hydrogen in this particular case, like you would see typically in hydrohalogenation. Your electrophile is going to be one of the halogens here, and that halogen would be going to the carbon that has more number of hydrogens to begin with. Okay, so if you have any questions on any of these, feel free to leave any comments in the section.